And we are back. All right, so we just talked about how the ionization energy changes within an atom as we keep on removing electrons from it. So successively, the first, second, and third ionization energies always increase, and there's a very, very large jump in between removing a valence electron and removing a core electron. So for magnesium, since it has two valence electrons, there's a huge gap, there's a huge jump in ionization energy from the second to third ionization energy. So now we should look at the trend, the periodic trend, in terms of both periods and groups. So in general, as you go from left to right across a period, first ionization energy increases. So the reason why we talked about atomic radius first is this is directly related, or it's similarly related to atomic radius. So if you remember from atomic radius, radius decreases as you go left to right. So the atom gets smaller and smaller. So that means the electrons, as you go from left to right, get closer and closer to the nucleus. So that helps explain why ionization energy, the energy you need to remove an electron, increases as you go from left to right. So the reason for that is the increasing nuclear charge caused by those number of protons. They're more attracted to the electrons outside the nucleus in that same energy level. Therefore, since they're more attracted to each other, electrons in that same principal energy level are more tightly bound, and therefore it's harder to remove them. So the stronger the proton-electron attraction is, the smaller the atom is, the harder it is to remove those electrons. So that's why from left to right, ionization increases. But then, as you go from top to bottom, as you go down a group, ionization energy decreases, because if you remember, if you go down a group, so if we're talking about group 1, so hydrogen only has one energy level, lithium has two energy levels, something like sodium has three energy levels. So the outermost electron gets farther and farther away from the nucleus as you go down a group. So that's why it decreases, because it's easier to remove an electron farther away from the nucleus. Even though there's more protons, even though the effective nuclear charge is increasing as you go down a group, the electrons are much farther away from the nucleus. So if you look at a graph, just like we did on Friday, as you go down a group, so if we're talking about group 1, ionization energy in general goes down. Same for group 18, the noble gases. Those go down. And then if you go across a period, so across period 1, 2, 3, 4, 5, and 6, in general, ionization energy increases. So you should know both those general trends. Across a period it increases, down a group it decreases. And then, if given an unknown element, you should be able to identify what group that element is in by looking at the numbers, the values of ionization energy, and see where the large jump is. So you should see for sodium, since it only has one valence electron, there's a large jump between the first and the second ionization energy. We already talked about magnesium. It has two valence electrons. There's a huge jump in the values, the energy you need to remove an electron between second and third, and so on and so forth. Aluminum has 3 electrons, so there's a huge jump from 3 to 4, and so on and so forth. So you should be able to identify the atom, what group an atom is in, by looking at that large jump in ionization energy as you go from removing a valence electron that's farther away to removing a core electron that's closer to the nucleus. Okay, however, if you look at the ionization energy values, there's a couple of exceptions here where it actually slightly decreases. So we're going to go over that right now. So you should label on your periodic tables as you go down a group ionization energy. decreases, and as you go from left to right, in general, it increases. So what is helpful, if you want to put on your periodic table, the largest ionization energy will be helium. So it's the smallest atom, and then if you add one more down here, francium, below cesium, that is the largest element, so it has the smallest ionization energy. Okay, so there are some exceptions here, where as you go from left to right, so from beryllium to boron, it actually goes down, and same thing with nitrogen to oxygen. So we're going to go over why that is. So as we go from beryllium to boron, we draw out the electron orbital diagram for boron. It has 5 electrons, so it has 2 in the 1s, 2 in the 2s, and 1 electron in the 2p sublevel. So if we're trying to remove an electron from boron, we would be removing this one from the 2p sublevel. So what happens, these electrons in the 2s sublevel provide shielding. Essentially, they're in the way, they're in between those 2p electrons outside the nucleus and the nucleus. So we say these 2s electrons shield that electron in the 2p sublevel from the nuclear charge from all the protons in the nucleus. Therefore, taking it away, removing it, is much less energy than you otherwise might expect. Then, the other exception here, as we go from nitrogen to oxygen, so now, if we look at the 2p sublevel of oxygen, it has 4 electrons. So the electron we would be trying to remove would be the one right here, the electron in the first orbital in the 2p sublevel that's spin down. So if you remember, for the exceptions for electron configurations for chromium, when 2 electrons are really close together in one smaller orbital, so 2p is a smaller orbital, those extra electron-electron repulsions in the doubly occupied orbital cause that, when we remove it, it has a lower energy than you might, lower ionization energy than you otherwise might expect. It's more easily removed than you otherwise might think so. So those are the 2 exceptions you should know. Beryllium to boron. Boron, the first electron in the 2p sublevel, is easier removed because the electrons in the 2s sublevel shield that from the nucleus, whereas this one, the doubly occupied orbital, when we remove that electron, we're getting rid of those close electron-electron repulsions. Okay, so you should be able to explain, as you go across a period, across a row, those electron repulsions are why there are some of those exceptions from beryllium to boron and nitrogen to oxygen. And it's similar for all the other transitions in the rows below that, so it's not only beryllium to boron, but it's also magnesium to aluminum below that, as well as phosphorus to sulfur below nitrogen and oxygen. So when comparing elements, atoms, you should be able to say which one has a higher and lower ionization energy. So sodium versus chlorine, the one with the higher ionization energy is chlorine. And don't just say, since they're both in the third period, don't just say, okay, chlorine's farther to the right. The reason why it's chlorine, it's smaller. Its electrons are more tightly bound, since it has a higher effective nuclear charge. It has more protons. It has 17 protons. Sodium only has 11. And all those electrons are in the same third energy level. So therefore, its electrons are more tightly bound to the nucleus. Whereas, if we're looking at lithium versus cesium, lithium has a higher ionization energy since it is smaller. Those outermost electrons, its valence electrons, are closer to the nucleus. They're more tightly bound since they're in the second energy level. Lithium is in the second row, whereas cesium in the 6th period has 6 energy levels, so that farthest most electron, a valence electron, is more easily removed. So now it can be a little more complicated when you are talking about second ionization energy. So if you look at lithium or beryllium, it's helpful to look at the electron configuration. So lithium 1s2, 2s1, whereas beryllium, 1s2, 2s2. So the second electron removed in lithium, the first one is the 2s electron. The second electron would be removed from the 1s sublevel, so the first energy level. Whereas the first 2 electrons in beryllium would be removed from the 2s sublevel, so the second energy level overall. So therefore, lithium has a much larger second ionization energy. You're removing that electron. You're removing a core electron, and that electron is from the first energy level, the energy level that's closer to the nucleus. So that takes much more energy than removing a valence electron or one from the second energy level. So when looking at a group of elements, you should be able to identify what has the largest and smallest first and second ionization energies. So if we have the following group of elements, and you're given these electron configurations, you should be able to identify first what element each of these are. And for each of these, we want to know what's the largest first ionization energy and what's the smallest second ionization energy. So first off, it's helpful to identify what each one of these elements is. So if you look at the first one, it has 10 electrons, so look on your periodic table. The element with 10 electrons is neon. The next one with 11, that's sodium, and then the one after that with 12 electrons is magnesium. Right, so the one with the largest first ionization energy is the one where we're removing that electron from the energy level that's closest to the nucleus. So in both sodium and magnesium, we would be removing an electron from the third energy level, whereas for neon, we are removing that from the second energy level. So therefore, neon has the largest first ionization energy. You're removing that electron from the second energy level that's closest to the nucleus. For the second part, the smallest second ionization energy. So if you look, neon, both electrons would be removed from the 2p sublevel. For sodium, the first one's removed from the third energy level, from the 3s sublevel. The second one is removed from the 2p sublevel, which is much closer to the nucleus. But if you look at magnesium, the first 2 electrons are moved from the 3s sublevel, so the third energy level. So therefore, magnesium has the lowest second ionization energy because both of those electrons are removed from the third energy level, which is farther from the nucleus than the second energy level. Okay, so that is ionization energy. The last trend is electron affinity, which is the opposite of ionization energy. Ionization energy is the energy you need to remove an electron. Electron affinity is the change associated with the addition of an electron. So if you're adding negative charge, you're producing a negative ion. Okay, so you're producing negative ions, and it's always for gaseous atoms. And in general, the trends are the same. Electron affinities their values become larger. They become more negative. So the reason why we say that they become more negative, addition of an electron is exothermic, meaning it releases heat, it releases energy. So the more negative that value is, the greater quantity of energy released. So the magnitude, even though it's becoming more negative, the magnitude of that value is increasing. And although there are exceptions to that, you don't have to know any of those exceptions like you do for ionization energy. So in general, as you go from left to right, it releases more and more energy. It becomes harder and harder to add that electron. And then in general, it becomes more positive, or the magnitude of electron affinity decreases as you go down a group. Okay, so it's the same trend as ionization energy. So make sure you label that on your periodic table. In general, as you go across a period, it becomes more positive. The magnitude of the value decreases. Then as you go from left to right, the value becomes more negative. So make sure you label on your periodic table as you go from left to right, electron affinity increases in magnitude, and in general, as you go down a group, its magnitude decreases. So since it becomes more positive, less energy is released, since the electron is added at an increased distance from the nucleus. So if an electron is added really close to the nucleus, it does not have much energy change, whereas if it's added farther away from the nucleus, it has a larger energy change. All right, that's all for today. See you next time.